that sname and p sharp together are is a super key for this relation. Right? Now what I want you to do is show that this is actually a minimal key and not just a super key. Okay, so I want you to think about this yourself first with your neighbors to see what would it mean if you want to prove that and what are the rules that you need to show. Any questions about the question? Right, get going.
That could be really bad. Considering how you have like two to be like something possible.
Yeah, what could be a way that I can prove that this is a minimal key? I already know that it's a super key, so I don't need to prove that everything is determined by this. How can I prove it's minimal? One way would be that if I take away one of the attributes from here, either I have sname on its own or p number on its own, this on its own cannot determine everything. And p number on its own cannot determine everything. Because if either of these on their own can determine everything, then that would mean this could not be a minimal key. Because I removed an attribute and I was still able to functionally determine it. Okay, so if you go through this, you can see that p number doesn't appear on the right-hand side of any functional dependency. So on the right-hand side, I don't see p number. That means that with these functional dependencies that I have, I cannot derive p number because, you know, the answer to none of these is p number. So I need p number to be part of my key. And similarly with sname does not happen to be on the right-hand side of any of these rules. So I cannot start with one and come up with all the different values. For sname, what can I get with sname? So with sname I can get city, I can get status. Can I get anything else? I don't see anything else. P number, what can I get with P number? P number gives me P name. So, and I can add sname to this one itself, and I can add P number to you. So most of you would agree that going through the proof of the rules that we had in order to prove whether something is a super key or whether it's a minimal key is pretty painful. And let's see if we can find easier ways of doing that. And what we're going to look at is closures of attributes. So X being a set of attributes, X plus is going to denote the closure of an attribute. And a closure of attribute is going to be the things which I can show that are determined by these two attributes. So here the closure of S name and P sharp, P number are these attributes. Here, so this is S name plus, this is P number plus, and this is S name and P number plus. So what I can do is, this is the rule, this is the algorithm that you can do it. When you start with X, first of all, in the closure of X, we're going to call this a closure of X, you're going to put X itself. So if I want to find closure of S name and P number, I can start with S name and P number. Let's switch these two around. So I'll have these two in at the beginning. And then what I'm going to do is, I'm going to go through all the functional dependencies that I have, and I'll check each of these, and I'll see that for any rule, if I have everything on the left-hand side as part of my closure so far, that means I can add the thing on the right-hand side also to my closure. Right? So let's actually do these again and use this rule. Okay, so I want to find the closure of S name and P number. I'm going to put in S name and P number to start off with. And then I'm going to go through all the functional dependencies that I have. For any functional dependency, if I know, if I have the left-hand side as part of my closure, I'm going to add the right-hand side to my closure too. So since S name is already in my closure, I can add city from functional dependency 1. From functional dependency 2, since I already know city, I can add status. From functional dependency 3, since I already know P number, then I can add P name. And from functional dependency 4, since I know S name and I know P number, I can add quantity. I cannot just go through that list once, because it might be the case that I can get something new from functional dependency 1 after I added something from functional dependency 4. So as long as you're adding new values into your closure, you might need to go through all of the different functional dependencies just to ensure you can't add anything else to that list. Okay, if you do the same for S name you're going to start with S name, then you're going to use FD1 to add city, and then you're going to use FD2, functional dependency 2, to add status. And for P number, first you're going to add P number, and then you're going to use FD3 to also add P name. Okay, and this is called the closure of S name, closure of P number. So if you want to check if something is key or not, is you find its closure, and if the closure contains all of the attributes, then that means it's a key. If none of the subsets, you find their closures too, and if none of their closures have all the attributes, that means it's a minimal key. Any questions? Right, first solve this and then I'll give you some different values to click for. Talk this one over with your neighbors.
So let's say you find the function b is then possible now and it
What's at the top now? I know, pretty much. A and C, then I need to B and E.
I'm wondering there are 3 different minimal keys for this question.
Yeah, I guess because then you
we have to decide whether to use
Just one
So it might be the case that the minimal key that you found is not out there. That means you can check those to see if those are in any of those remains.
The only way to have to represent B is to have B
For a second.
They can be
Okay, 5, 4. People just joined us. 3, 2, 1. Okay, so let's do each of these. A, B, D, E. Is this a super key at least? So you can add A, B, D, E because you already have those. And what else do you need? You need C you can get from the first dependency. D gives you C, so you can add C here. This is a super key at least. Is it a minimal key?
No.
Why not? Functional dependency 3 says that D gives you A. So B, D, E on its own will give you B, D, E. You're going to use functional dependency 3 to get A, and once you have these, it's similar to here, and you get C. So since you found something smaller than that, then this is a super key but not a minimal key. Let's do BCE. So let's add BCE in first. So C and E, I have those. That's going to give me A. And A and E, I have those. That's going to give me D. So this is at least a super key. Is it a minimal key? What do I need to do to prove this is a minimal key? I need to find BC closure, I need to find BE closure, and I need to find CE closure. And I have to show that none of those will have all of these values in their closure. I think most of you got this one right. Does anyone want me to go through the rest of this to make sure that they're getting it?
Yes.
Alright, let's do BC plus. So let's start from the top. Can I use first functional dependency? No, I don't have D. Can I use the second one? No, I can't because I don't have E. I don't have D, I can't use the third one. I can't use the fourth one because A, I don't have anything. So the closure of BC is just going to be BC. What about BE? Can I use the first one? I cannot. The second one, C and E, I don't have neither of those. I can't use any. D, I can't use because I don't have that. And A and E, I don't have those, so I don't get anything else. Can CE be a key? That one would have been easy to see because B is not out there at all. Since B is not part of any of your functional dependencies, there's no way that you can get it through a functional dependency. So B needs to be part of your key in order to be in its closure. Because there's no other way you can get it in that closure. Since none of these are a key and this is a key, that means this is a minimal key. What's wrong with CDE? I can't get B. Any questions? If you're wondering, ABE, BCE, and BDE are all minimal. Okay, so let's not forget the bigger picture, right? We're going through all these algorithms to come up with a way that I can take this table and decompose it to make sure that there are no anomalies when I'm trying to update, insert, or delete. So wouldn't it be nice if we had some rules that would tell us how we can decompose this? And this is why we're going through all this closure, finding keys, and so on and so forth. Role of FDs in your database is to show you redundancy. Okay, so when my database is telling me A determines B, that's telling me that you might have a redundancy. If I don't have any FDs in my table, I don't have any redundancy. Normalization is a process which we're going to go through that's going to take us from one set of tables and it's going to transfer them to a set of new tables where I'm not going to have these anomalies in those new tables. Okay? And we're going to say that the new database after that translation is normalized. And we have different normalizations that we're going to look at. Why would you have one rule when you can have four? So we have four different normalizations we're going to look at. First normal form, 1NF, 2NF, 3NF, and boycott normal form, which is BCNF. And again, the main reason we're going to go over these normalizations is for you to be able to have a bunch of tables where those anomalies that we talked about before are not part of your relations. 1NF and 2NF we're not really going to talk about a lot. 1NF only says that each attribute in a tuple has one value. Okay, so I cannot have a full data structure instead of one of my attributes, or a linked list, or an array. One attribute, which is name, can contain one name. It cannot be a data structure of names. BCNF is actually never used neither, because we moved on to the other two. But it says that a relation is in 2NF if for every x and y, if x is a minimal key and y is a non-key attribute, so what you have in y is not part of what you have in x, it's different attributes, then no proper subset of x determines y. So if house number, street, and postal code is a minimal key, so house number, street, and postal code determine province. You cannot have postal code, which is a subset of this, also determine province. So here, X is the set of house number, street, and postal code, and Y is province. Therefore, with this, you cannot have this rule if this is in 2NF. And again, don't worry much about 2NF. It's not actually mentioned at all in the textbook, and we're not going to be mentioning it much neither. So it was a jumping from 1NF to BCNF that just went through 2NF.
What 2NF means?
Sorry?
What 2NF actually means?
Normal forms. So second normal form. First normal form, second normal form, and third normal form. Okay, so let's look at BCNF, which is boycott normal form. Our friends Raymond Boyce and Ted Cott from before sat together and came up with this and resolved many problems in the world. A relation is in BCNF if for any set of attributes X that determine B, this is a non-trivial dependency, then X is a superkey for R. And yet, this is why we needed superkeys. Because when we're talking about BCNF, we're talking about this X here needs to be a superkey. And this must be true for every such dependency that we have in our table. Just a reminder that a dependency is trivial if something that's inside the left-hand side is also on the right-hand side. So if I have city and province and that's determining city, this is a trivial dependency. And here I'm only talking about non-trivial dependencies. In English, what this means is that if I have some attributes functionally determining a few of the other attributes, it has to be the case that they determine everything else, and not just a subset of them. If postal code is finding province, then it should also find everything else in that table. Okay, so this is the way English way of saying the same thing. So let's say this is our relation, the schema for our relation, and these are the functional dependencies that we have. Is this in BCNF? Postal code is determining city and province, but postal code is not a super key. Okay, so since postal code is finding some functional, some attributes, but it's not a super key, then this is not in BCNF.
What do you mean by non-trivial?
Non-trivial basically means anything non-boring that we discussed. Anything where the right-hand side is contained on the left-hand side is trivial. So here, city is here, so that's why it's trivial. So XB, this could be our postal code is determining B, and postal code is not a key, therefore this is not an BCNF. Any questions? So the question is, how do we take a table and how can we end up with BCNF after we do the transformation? Bonus fact, everything that has two attributes is in BCNF. So it's not going to be a recursive procedure which is going to be taking forever. Because you know, as long as you're decomposing, if you get down to two attributes, it's in BCNF. Why is it in BCNF when you have two attributes? Because only one of those four things could happen. Let's say you have two attributes x and y. Let's say there are no functional dependencies. If there are no functional dependencies, then nothing can go wrong, so this is in BCNF. Let's say you have a functional dependency that x gives you y. That means that x is a key for this relation. Since x is a key and a super key and it's determining y, that's fine. This is in BCNF. If you have a functional dependency which says y determines x, that means y is your super key and your key. So that's fine again. You have the super key finding non-trivial attributes. Non-trivial functional dependencies, I'm sorry. That's also fine. And the last option would be that both y determines x and x determines y. That means that both of these will have the same value all the time. So that means both x or y on their own are candidates to be key. They're both minimal keys. Both of these, x is a super key, y is a super key, so this is still in BCNF. So you know that if you get down to two attributes, your table is in BCNF. Otherwise, you can look at your table and you can see if there are any violations on this table being a BCNF. We need to get rid of those violations by decomposing. So I'm using the word decomposition a lot. Let's see what that means. A decomposition of R would replace R by two or more attributes, such that all of the attributes that are part of R have to be contained in one of these other new tables that I have. And also, so every attribute needs to come up in at least one of the tables that I'm decomposing. And intuitively what this means is that we want to store R, but instead of storing R, I want to store a bunch of other tables. Okay, so I can take this example again with the address, and I can decompose it into address and postal code like we saw before in order to get rid of some of the problems that we have, the anomalies. But how can we decompose without losing information? Let's have a sneak preview to near future where we're going to be talking about joins, and let's see what that means. I can take two relations, R1 and R2, and I can join them together. So R1 has A and B, and R2 has B and C. If I'm doing the join of these two, that means that whenever there is similar value in B, I can put this part of the row and this part of the row together to create a bigger row inside this new table. So I have 1, 2, I have 2, 3. That means I can have 1, 2, 3 in this new table. I'm joining these two on the value of B to get one new table, one new tuple in my new table. I have 4, 5. I have 5 here with 6. So 4, 5, 6 is another tuple. I have 7, 2. Here I have 2, 8. So that gives me 7, 2, 8. But what this means is that I have 1, 2, and I have another 2 down here as well. I have 1, 2, and I have 2, 8. So that means I can have 1, 2, 8. And with this 7, 2, and this 2, 3, I can have 7, 2, 3. Okay, so when I join these together, it's not the case that I have to end up with 3 new tuples. I could have more than 3 tuples. Because each of these rows that finish with a B are now merging with 2 tuples from B in order to get 2 new tuples in my new join table. Any questions about joining? Now, let's look at lossless join decompositions. Informally, what we mean is that if we decompose a table into 2 tables, and then we join it back together, we want to end up with what we started with. We don't want to create new information, we don't want to lose information. Okay? So I have R, now I'm going to decompose it into an X and a Y part. I join the X and the Y part back together, I want to get back R, and nothing more. So let's say I have this table, and I want to decompose it into A and B. When I decompose this, I'm going to keep the A values and the B values on this side. I have 1, 2, I have 4, 5, I have 7, 2. I'm going to keep this on this side. And here I'm going to keep the B and C's, that's 2, 3, 5, 6, 2, 8. When I join them back together, I started with 3 families here, living together happily. When I join this back together, now I have 5. Right, so now let's see what happens. I have 1, 2. This 2 could be joined with 2 different rows, with 2, 3, and 2, 8. 2, 3 I had before, that's fine, but 1, 2, 8 is something that I didn't have before, and it's just being introduced now. So I decomposed, I put it back together, I didn't end up with what I started with. It's always the case that this table that you end up after you join things back together always contains everything that you have in the first table. Okay? So that's something you don't need to worry about. All those 3 values always going to end up there. The other way around is not always true.
When you decompose, could you also get AC? Or is it just...
Yeah. When you decompose, you can get AC and AB, or AC, BC. You can decompose in any method that you like. Any questions about this? Can anyone intuitively see why this is happening? So currently, this is not the case 2 could end up with a 3, and this 2 could also end up with an 8. Because B is not functionally determining C. I have 2 different values for 2. 2 could end up with 3, and 2 could end up with 8. If B was functionally determining C, this would have not been something that I would have encountered. Okay, so when I decompose, I want to take those functional dependencies into consideration, that when I decompose and when I join back together, then I get the right answer. Was there still a question?
Yeah, it can be really bad stuff to end up with something like 1 to 8. Because I'm thinking of example, if it's my student ID, my last name, and her grade is better, so I end up with...
So this is really bad. You do not want this to happen. Because exactly, you're right. That means that your student ID with someone else's grade is going to go together, right? And this is not something you want. This information was not true in your table, and you don't want to be creating that information. Some of you wouldn't actually mind. I mean, there might be a good grade in your transcript after we screw up like this, but not all of you.
So what is the solution for decomposition then?
The solution is you listen to me and do the algorithms that I tell you, so your decomposition doesn't turn out to be like this. Okay, so this is the motivation of why we can't just decompose randomly, and why we need to know functional dependencies, and why there are all these rules. Any questions? Okay, so let's see how we can decompose. Let R be a relation. Then we're going to take a functional dependency that is violating BCNF. So we're going to take one of the dependencies where X is not a superkey. Okay, so that's currently violating my table. I'm going to decompose based on this functional dependency. I'm going to get 2 tables. In one of them, I'm going to put X, which could be a set of attributes, and B. In the other table, I'm going to put everything else and X. Okay, so the rule is you have a table, you have a functional dependency which is violating BCNF. You pick that, you decompose your table into 2 tables. One is going to be having values in X and B. The other is going to be everything else and X. Let's see an example. So let's say I have a relation ABCD with functional dependencies BC and DA. Is this in BCNF? That's the first question. Well, to know if something is in BCNF or not, I need to find the superkey. Right? So let's find the key. Let's find A closure. Closure of A is just A. A doesn't give you anything else. Closure of B is B itself, and with the first functional dependencies, you can also get C. Closure of C, it's just C. You can't get anything else. Closure of D is D itself, and A you can get with the second functional dependency. The closure of BD is going to be BD, and then with B you can get C, with D you can get A. So BD is your superkey. BD is your superkey. You have a functional dependency which says B determines C. Is B a superkey? It's not. So this is violating BCNF. Since B is not a superkey, and B has a functional dependency with C, then that means BC is violating my BCNF. What do? I decompose. How do I decompose? The violating functional dependency, x functionally determining b, x is here b, and b is c. I'm going to get one table with just b and c. I'm going to call this R1. And everything else, which means a and d plus b, I'm going to put in my second table. So now I'm going to end up with R1, which is b and c, and R2, which is a, b, d. Any questions so far? Is R1 in BCNF? Anyone? Alex?
Yes, it is.
Why?
There's only two.
Two attribute tables are all in BCNF. So that one's good. You don't need to worry about it. Is R2 in BCNF? To know whether R2 is in BCNF or not, we need to know what the key or superkey for BCNF for R2 is. Right? So I have A, B, and D. D on its own determines just A and D and does not determine B. So D is not a key. I need B and D together to determine all A, B, and D. Right? So still, my key for R2 is going to be BD. D is determining A. So it's violating my functional dependency because now D is not a super key and it has functional dependency with an attribute. So D functionally determining A is currently a violation to my to BCNF in my R2. What do? I decompose. So DA is violating this because D is not a super key. DA is the violating functional dependency. So we get two tables. In one we're going to have D and A. In the other we're going to have B and D. So I had R1 before. R2 was further decomposed into R3 and R4. The final answer would be, for me, if I want R to be in BCNF, I'm going to translate it to R1, R3, and R4. So now instead of instead of R, I have three tables, R1, R3, and R4, which are now in BCNF. Why are you going through all this algorithm? To come up with R1, R3, R4, so this doesn't happen to you. If you just randomly put attributes into your decomposition, when you join it back together, you're going to get bogus tuples like this. If you're using this algorithm, what this is guaranteeing is that when you join these back together, you're gonna end up with what you started. Any questions? Okay, so I want you to give this a go. This is also in your slides. So if you're having trouble, look at those slides. If not, try doing it yourself first. And these are the rules in case you forget. Alright, let's do it together. Okay, so first question. This is a relation. Let's find the closure of A, B, and C. I'm sorry, A, B. Closure of A, B will be A, B, and also C. And closure of D is going to be D, E. Is A, B a superkey for relation R? It is not. So it's violating BCNF. So we decompose. The rule says A, B determines C. So A, B is my X, C is my B. I have one table which is going to be A, B, C. I have another table which is everything else plus my X, which is going to be D, E, A, B. Okay, so I'm gonna be left with R1, which is A, B, C, and R2, which is A, B, D, E. Now I need to check. Is AB a superkey for ABC? For R1. AB determines all A, B, and C, so AB is a superkey for R1. So I don't need to decompose R1 any further, because this functional dependency, which is relating to this is already a superkey. Is D a superkey for this relationship? D is not a superkey for R2, so I need to further decompose it. So AB is a key, D is not a key for R2, so we decompose further. How are we going to decompose it? This is the violating rule. I'll take D and E and put those into one table, and A, B, which are the other stuff, and D, I put these into one table. I've decomposed R2 now to R3 and R4, A, B, D, and D, E. Now we look at these again. Is A, B a key for this one? So R4 is in BCNF because there's only two different values here. R3, AB functionally determining C, C is not part of this relation anymore. Right? I've taken C out of here. So the functional dependency, which were giving me trouble, does not hold in this relationship anymore. Because C is not part of this relationship anymore. So the question is, are any of the functional dependencies that I have violating R3? And none of those functional dependencies are violating R3. This is a problem that we're going to come back later when we talk about third normal forms. But for now, I have now three tables, R1, R3, and R4, and they're all in BCNF. Any questions? Right, let's leave it here. So the algorithm isn't that difficult, it's pretty trivial, but you need practice. So make sure that you get some practice on BCNF problems so you feel comfortable with it.